Alright, Chapter 4. Again, Chapter 4 and Chapter 3 are extremely important to any of you that are going on to business calc or calculus and other math classes like those. So we're going to start talking about exponential functions. And an exponential function in its general sense is this equation right here where you have f of x is equal to b, which is some number. Okay, it has to be a number, and that number cannot be equal to 1. It has to be greater than 0, and I'm going to ask you why, and if I don't remember to ask you why, then I'll do it on the Zoom session. And the b is the base, and again it's a number, and the x is a variable, and that's the exponent. So nothing crazy like x stands for exponent or anything like that. So what I want to do, and this is what I despise more than anything, is to actually plug numbers in. Now I've already done the substitutions, so I'll just want to make sure that you understand what I've done. So let me do it with a little bit different color. So when you're doing this calculation, you're figuring out 2 to the third power gives you 8. And it's the same thing for each of these. And then you need to remember that 2 to the 0 power is equal to 1. And at some point, I'm going to do a quick review of your properties of exponents in case you don't know them. And I might even give you a little explanation. But the other thing you need to remember is that a negative exponent means to take the reciprocal of the base. And so that's where the 1/2 comes from. So if you get the idea, I'm just going to jump to the last one. And this is 2 to the negative 3, which is a 1/2 to the third. That's going to give you the 1/8 that you see. Now, I need to go ahead and erase those calculations. So if you want them, you better pause me. But again, the calculation, well, let me just do this over here. If you do 1/2 to the third, that's going to be 1/8. If you do 1/2 to the 0, that's going to be a 1, just like before. And if you do 1/2 to the negative 3, that is, again, take the reciprocal and raise it to that power, and that's where the 8 comes from. So what I want you to see there is where the numbers come from by substitution. But we're not going to do it by substitution. You should be aware that I hate substitution. I only do it to introduce certain ideas. But I'll need you to remember these numbers when I go to the next slide so we can talk about the transformations, which, oh, by the way, it's the same transformations that we did in Chapter 2. So if you know about that, you'll be good. I'll get to that in just a second. So let me get a different color. I see if I can leave that on there, and let's graph the points that we have. 3/8, all right, is right here, and 2/4 is located right here. 1/2, 0/1, -1. This is a negative, by the way, over here. I just realized, but -1 is going to be a 1/2. -2 is going to be a 1/4. -3 is going to be an 1/8. And again, if you think about it, if you take a number that is like a 1/2 and you raise it to the 50th power, is it equal to 0? No, it's not equal to 0. So this graph is never going to touch that x-axis, which guess what that means, gang? I hope you have fond memories of this, but there's your graph. And what I mean by fond memories is that you have a horizontal asymptote, and that's going to be an important feature that I want you to include when you graph. And the horizontal asymptote is the x-axis, which you know to be y equals 0. So there's 3 things to remember. There's 3 things to commit to memory for this equation. One is the horizontal asymptote. The second is that unless I get crazy, and guess what? I'm not going to get crazy. We're going to stick with the basics that you're going to see in these examples. Then your number right here is just going to be a number like you see with the 2 or the 1/2 or some other number. It's not going to have anything else in front. We're not going to worry about a 5 times a 2 to the x or anything like that. Now, if I see you in pre-calc algebra, then yeah, we'll worry about that. I'll talk to you about that. Right now, I just want to make sure I get the basics down very firmly. And so the other thing you should note is that if you had a man walking from left to right, guess where this man is headed? This man is headed up as he walks from left to right. And this is him going left to right. Guess he broke a leg. But anyway, so you need to remember the shape. And this is going to happen anytime that this base right here is bigger than 1. Now, last fall I said something about proper fraction, improper fraction, but Shayla and Alexis said that, or Alexia said that caused them problems. So I guess I'm not going to try that on you. Just know that the base is bigger than 1, and I'm not going to talk about any kind of proper, improper fractions. I'm very tempted. That was the first time it ever caused a problem, but it definitely caused a problem for them. So anyway, let's just stick with numbers bigger than 1 or smaller than 1. We'll talk about in the next example. So we're going to go to red, and we're going to plot points again. And when we plot points, I think I need to erase a little bit because this is in my way. So hopefully you've had enough time. If you wanted to jot that down, you could. I'm counting. There's 5, 6, 7, 8. All right, so -3 is going to be an 8. There's that point. -2 is going to be a 4. -1 is a 2. 0, 1. 1, comma, or negative, excuse me, 1, comma, 1/2. I'll get it right eventually. 2, comma, 1/4, and then 3, comma, 1/8. So again, I'm moving my iPad that I can't do when I'm standing at the board. And my graph is going to do something like this. And again, it does not touch that x-axis. It will get closer and closer to it, and you still will have the same features. I think I'm going to use a different color this time, but you still have the same features of a horizontal asymptote at y equals 0. You still have that point that's at 0, 1. It's kind of like your vertex that I'm looking for. And then guess what's going to happen to Professor Plum here? This person is going to be going downhill. So this function is decreasing or going down. So I had a cough, sorry. So anyway, there are the 3 features. The shape of it, this point that we're going to use like a reference point, and this horizontal asymptote. That's not AA, that's HA. So those are the things you need to commit to memory. If I've converted some of you to cards, like good old Natalia, then you would have a card where you have the equation on one side and the base information on the other side with the actual shape, and do the same thing over another card, and you would remember that basic shape. Now, there's one more thing I want to do before I forget, and I need another color to make this work, I guess. So I guess we'll do burnt orange here. And that's the domain and range. The domain for these kinds of functions is going to be all reals. It's supposed to be a script R right there. There's no restriction because you're not dividing by 0 and you're not taking the square root of a negative number. The range, however, are going to be y values that are greater than 0, or if you prefer, parentheses, oops, not an 8, but infinity, I'm sorry. All right, and the thing that's interesting about this, at least I think it's interesting, you may not, but anyway, is the domain is still the same, and the range, is still the same. So please make note, why is this range what it is? Why is 0 the key thing? What's going on here? It's because of the horizontal asymptote. And so when we start graphing the other shapes, I'm going to make a note to you about where you should start and why. And I'll give you a little history about it. There's always a history lesson in one of my classes of what's worked and what hasn't worked before. So I'm going to pause for a few seconds if you want to pause this, and then I'm about to move on. Time's up. All right, so I need to talk to you about what's going to happen here. And honestly, I don't know if I really want to write all the numbers. I'll write a few of them, I guess, once I start doing the chart. And here's what I mean. If you have a -2 to the x for your y, then if you put numbers in, let's say just like a 3, just to see what happens, then this is the opposite of 2 to the third, and you have to raise it to the third power first. And it's the same thing if you have this. You've got to square it first. It's like having a parentheses around that. So basically, all of those numbers that we've been talking about on the other side are just going to be negative versions of the same numbers. So what does that do to your graph? It's going to rotate it over the x-axis, just like we talked about back in Chapter 2. So whatever you learned in Chapter 2 is useful for what you're doing here. So let me graph it with a different color, but that means you have a horizontal asymptote that doesn't change, but the point is now down here at 0, -1. Now remember, for a 2, it does this, and it goes up forever. So when you take the opposite of that, you see how it's getting close to the horizontal asymptote up at the top, or to the left, I should say. Then it's going to do the same thing, but it's going to be below, and your graph is going to do something like this. And honestly, that's all you have to do. I need to see the horizontal asymptote, I need to see this point, and I need to see the appropriate shape. I don't care about plugging any numbers in, not even like I made you do in quadratic functions. Alright, so if we examine what's happening here with the values, again, I don't want to, well, just remember what's on the other side, and let's just say if I have a 2 to the x, and then I have a 2 to the x plus 1, I don't want to change and look at all these numbers and see what happens. I just want us to do this. In other words, if I put in a 1, a 2 to the first is going to be a 2, and so I'm going to end up with a 2 plus 1, or a 3. And more importantly, I want to put a 0 in there, and 2 to the 0 is equal to a 1, and 1 plus 1 is going to be equal to a 2. 2. Now what happens to the other numbers, and I don't want to get too carried away, so let's just do the negative 3. So 2 to the -3 we've talked about as 1/8. So I have a 1/8 plus a 1, I get a 1 1/8. So what is the effect on our graph when this is all said and done? And by the way, I want to erase that because I don't want that to be anything that you think is part of your graph. But anyway, back to this one. If we start graphing the points, the horizontal asymptote is shifted up 1, because it's never going to get smaller than a 1. And so the point that used to be at 0, 1 is now going to shift up, and then you're going to have the increasing shape that we talked about before. So here's what I'm going to pound on my iPad about, since I can't pound on the board. The first thing you do, okay, the first thing you graph is the horizontal asymptote. So let me tell you historically why that's the case. If that shifts up or down, the biggest mistakes that I saw students make, and I'm going to do it wrong, and I'm going to go ahead and erase it, they would do stuff like this. And that's just flat out bad, and I'm going to take it off of there, because it doesn't really tell you what the range is going to be for that thing, because that horizontal asymptote shifting up is going to affect the range. So when I started telling my students to do this first, the mistakes that I just showed you in green just a moment ago, they went from happening 10 times to maybe happening once or twice. And it's because people were absent, or they slept, or they weren't doing what they're supposed to, and they wandered in late. And so in your case, you're not watching the videos, or you're not listening to the Zoom sessions, and then I have no sympathy for you if you draw it below that. But the rest of you, you should know that the first thing I draw is this. Then I take that point that's going to be 1 unit away from my horizontal asymptote, and then I'm going to draw the appropriate shape, which is the increasing shape that you see here in red. Okay? Now, the next one's a little bit more of a pain in terms of doing substitutions, so I have to be a bit more careful about what I do, and I don't want to do them all again. And since you see the 2 to the x right there, I think I'm not going to bother messing with that. I just want to put in some numbers like a 2, a 1, a 0, and a -1, and maybe that's enough. Well, maybe I can fit one more in there. And I want us to look at what happens here. So if I have 2 to the 2 plus 1, that's 2 to the third, I get an 8. That 8 is happening at a different spot. If I put a 1 in there, I'm going to get 2 squared, and I'm going to get a 4. And if I put a 0 in there, you don't have that point that's 1 unit away. You actually have a 2 to the first, or 2. So where does this point end up? Look what happens now. If I put that negative 1 in here, then I get 2 to the 0, and I get a 1. So this point, this is the one that I want you to see more than anything. This point right here is now equivalent to what you had before when you did a 0 and a 1 right here. I just butchered that 1 up. So it's going to affect the location of this point. Or in the other basic shape, it's going to affect the location of this point. And how is it going to affect it? That's what we need to talk about. Well, the thing that you need to realize, by order of operations, I don't have to have a parentheses there, but there might as well be a parentheses there, because if you didn't notice, I always added before I ever raised anything to the power. So that's like being in the parentheses. So that's the same thing that we talked about back in chapter 2, where you ask yourself what makes that equal to 0, and when you answer that question, that is a left shift. Now, what does that do to the horizontal asymptote? Well, if you take a horizontal line and you shift it to the left 1, does it change the line? No, no way. What's it going to do? It's going to take that point that used to be here, and it's going to put it 1 unit to the left, and then you're going to have this increasing shape, and you're done. That graph is now going to shift to the left 1 unit. That's the effect of what's going to happen with that x plus 1 that's in the exponent. It's like being in the parentheses. All right, so soak on this for a minute or a few seconds, and I'm going to move on. Oh, one more thing before I move on. I lied. And that is the domain and range. The domain here, the domain for all of them isn't going to change. The thing that will change is the range for each of these. And let's just do that in blue. The range for this is going to go from negative infinity to 0, or if you prefer, y is less than 0. For this one, the range is going to be y greater than a 1, or it's going to be 1 to infinity. And then as far as this one's concerned, nothing has changed. The range is the same thing as your basic shape from before. That, or if you prefer, that. Don't really care. So the thing... All right, pause for a phone call.
Hey, Mr. Soash, my name is Marcel, and I'm with...
Okay, well, I guess I should have talked to him, but I didn't. So moving on. So now I want to talk about how to graph some of these other shapes. And so I'm going to have to do this little spot down here at the bottom. I'm going to do the different varied shapes so that you can see what happens. And I'm going to do them kind of small, but then I'm going to have to erase them when I do the other examples. So when you're doing this problem, you've got to ask yourself, is 5 bigger than 1? And the answer, of course, is yes. So you know your basic shape is going to do this with that horizontal asymptote right there. All right, back to work here. So the negative then, if we do that part next, is going to flip it over the x-axis and look something like that based upon our earlier discussion. And then I always like to do the up or down shift next, so I intentionally do this part right here with the +2. And so what will that do? It will cause my horizontal asymptote to go up 2, and my graph is going to do something like this. So when I graph the answer, which I'll do in red up here, then the first thing I draw is going to be this horizontal asymptote at y equals 2. And then I'm going to take that point that used to be here, and because I asked myself the question, what makes this equal to 0, I know that my shape, actually my point is now down below, I have to go here, but that point now is going to shift to the right 3, and so that point is now located here, and that's what's going to happen to my graph, and that's the answer for that one. So I'll let you look at it for a second, but I need to erase all the stuff that's in blue. let you listen to me erase. Okay, so if we do the next one is the g of x. I need to do it in a different color. Let's do green. G of x is equal to 2/7 to the x power. Well, that fraction is between 0 and 1. And I just realized I didn't write that in regards to what the base is. So I wrote this one, if the base is bigger than 1, it does this increasing shape as a basic shape. And if it's between 0 and 1, then it's going to do this decreasing shape that you're about to see. And this decreasing shape is this one with the same horizontal asymptote. Alright, so the next thing I would do is the plus 3 that's outside of the exponent. So that's going to cause this graph that you see to your left in green to shift up 3. And you're now going to have a horizontal asymptote at y equals 3. And then finally, what do I do about the rest of this after I graph, oops, wrong one. I graph the decreasing shape. Well, when I graph this one, I'm going to move 3 units up for the horizontal asymptote. I'll eventually say it correct. And I ask myself, what makes this equal to 0? And that's the -2. So my point is going to shift over here, and I'm going to have this decreasing shape that you see. And that's what your graph is going to look like if you were to do that g of x equals 2/7 to the x plus 2. Alright, so next example, and let me just erase this. It's interesting, I can do it with my finger or I can do it with the pen. Alright, so let's get a different color. I don't know, let's do purple, I guess. So when we look at this h of x, and you look at the 7/3, well, that number, 7/3, is bigger than 1. So the shape of it's going to be that same increasing shape that you see for a 2 to the x power. It's this one right here. And I only have one more thing to do, so I actually can go to the answer. This -4, it's not in the exponent, so it's going to shift down 4. I'm going to draw that horizontal asymptote first. I'm going to draw that point that's going to be 1 unit away, and I'm going to draw that same increasing shape. So just because you see a fraction, you have to look at the value of that fraction. You can't just look at nothing or anything. Alright, so that's the graphing. So I will wait for you to look at that, and then I'm going to move on to the next thing, which is not even in your book in section 4.1. It's actually in section 4.4. Alright, so what you see now is a worksheet that has 8 questions, and these answers are correct, so don't come back to me later in a Zoom session and say that these things are not correct. They are correct. You did it wrong. So I'm going to show you examples like these. I'm not going to do these right now unless you ask me about it in a Zoom session. So it's up to you to do this. This is on Canvas, but I figured I'd at least show you this way what it is. Now, before I move on, and this is a nice convenient place for me to show it, you need to remember your properties of exponents. When you multiply like bases, you add exponents. When you divide like bases, actually I should have x to the m over x to the m, that's typically how it's written, you subtract exponents. If you have x to the m raised to the n, you multiply exponents. Okay, those are the basic ones. I call those, I guess you could say, the big 3. But you need to remember things like this. If you have the nth root of x to the m, that's the same thing as x to the m divided by n. And if you have x to the -1, that's the same thing as 1 over x to the first, which is the same thing as just a plain old 1 over x. And if you have x to the -n, this is the same thing as a 1 over x to the n power, and that's really the same thing as 1 over x to the n. That's an n right there, gang. So these are your properties of exponents that you're going to desperately need to know to be able to do this worksheet right here. So I've got a set of examples that I'm going to do, and the idea is the following. So let's move on. All right, the basic idea is this. If I asked you a question, and I haven't lost my mind, trust me, I haven't, even though this process is driving me crazy. If you saw a question like that, and I ask you to solve for x, there's not anything for you to do. It's a logic step. And so I've come up with this silly, stupid, squiggly line that you see right here, just to be an indicator to you that I didn't do anything algebraically. I just said, well, if that's going to be true, as long as the bases are the same, then the exponents have to be the same. There's nothing special to do to that thing. And so that's what is going to be the key thing. When you see a squiggly line, I'm doing a logic step. In one of my classes one time, I always jokingly said it's squiggly line time once we get to the one spot. And I need to talk to you about when that will be. But I'm going to erase this because I just set one slide up for this set of examples that I'm going to show you, and I got 5 of them that I want to do. All right, so the idea then is, what if they're not the same? What if you have 4 is equal to 2 to the x, or if you have something else like a 64 is equal to 2 to the x? Let's go back to the just the 4. What you have to do before you can do squiggly line time is you have to rewrite these numbers that you see, the higher numbers, to a smaller number power. So we all know that 2 to the second is a 4. And now here it is, squiggly line time, that 2 is equal to x, and you got your answer. And so if I was to ask you to do that one that I threw or pulled away, the 2 to what power is going to be equal to a 64, you got to figure out what that power is, because you can't do it any other way until I get to section 4.2. But this is a key thing that I don't know why in the world the author puts this process that we're talking about now in section 4.4. If you're going to understand 4.2, you got to understand what I'm showing you here. Well, if you don't know what 2 to what power is for 64, I just kind of multiply on. I know that 2 to the third is 8, 2 to the fourth is 16, 2 to the fifth is 32, 2 to the sixth is 64. That's what I do in my head, but that's what I do. So when I erase all those things underneath, because I've written the 64 as, go away. Getting messages on my iPad I don't want to see. Because we have the same base, I know that 6 or x is equal to 6, and I've got my answer. So that's the key idea. You have to make it so it's the same base. And sometimes you have properties of exponents that you're going to have to worry about as well. So let me show you one more basic example before I get fancier. So let's suppose that I've got a 4 to the x is equal to a 32. Well, you can play with it, but there's no 4 times some power that you're going to figure out in your head is going to give you a 32. So what should I do? Well, you should go backwards to the smaller number. 2 to the second raised to the x power is equal to 2 to the fifth, if you remember what we talked about before. And before you can do your logic step, you have to use all properties of exponents, which we've already talked about. And so power of a power means you multiply them. And so you end up with 2 to the 2x is equal to 5, 2 to the fifth. Now it's squiggly line time. Now you can set the exponents equal to each other and divide by 2, and you get 5 halves. And yes, Juliana, 2.5 is what you also can write. I remember you didn't like that when I did that in that Zoom session. Just teasing you. Okay, so if there's any properties of exponents, you've got to go ahead and do them. So let me make up one more, and then I'm going to go ahead and show you some other examples then that we're about to do. So if I had 3 to the x plus 5 is equal to a 9, then I need to try to match these so they have the same base. There's nothing to do with this one. and 9 is the same thing as 3 squared, so I can logically do my logic step and set them equal. And so I can subtract a 5 from both sides, and I get my answer as x equals a negative 3. And there's your answer. Okay, so these are the basics. I'm going to give you a moment to copy them down, but I have to erase all of this stuff. Because like I said, I've got 5 examples that hopefully will help you do that 8-question worksheet. And if you decide to go visit section 4.4, if I can remember exactly, I think it's like problems 1 through 24 or something like that. And yeah, I know you're going to ask me to take pictures. All right, so time to erase. You've paused me long enough. Glad you're not seeing my face, because some of you probably paused me with my mouth open or something stupid. Alright, so I'm going to use a different color, and actually I'm going to erase I should have just erased the whole darn thing, big dummy. I can do that. I'd have done it a heck of a lot quicker. Let's go back to our black color, and let's talk about examples. 4 to the x is equal to a 32. Oh heck, I just did that one. Alright, let's change that one. Let's do something different. Or else I did something awfully like it. So the basic idea, again, if I do something that's comparable, let's do something with 5s. Let's suppose that I have 125 is equal to 25 to the x power. Alright, so 5 to the third is 125. 5 squared is 25. But I've got to do my property. Okay, my property is power of a power, so this is 5 to the 2x. And now there's no other properties that I have to do. So that means I can set the exponents equal. It's squiggly line time. And then I just solve this, and I get x to the 3 halves. Let's try that 3 halves again. Or if you prefer, 1 and 1/2. Sorry, Juliana. Alright, so there's another example like the one I just did. So example 2 that I want to do is this one. It's 2 to the 2x plus 3. Set it, but I didn't write it, is equal to a 32. So there's nothing to do to the left side, so I'm going to recopy that. And then the 32 is 2 to the 5th. So there's no properties to worry about, so I can do my squiggly line, and I'll have 2x plus 3 is equal to 5. Subtract 3 from both sides, and I get 2x is equal to a 2, and x is equal to a 1 when I divide by 2 or multiply by a 1/2. So there's a second example. Alright, let's do another example. And then I'm going to have to erase this, because like I said, I only set up one screen before I do the next set. I tried to sort of plan my lecture ahead like I don't do in class, where I ad lib all the time. Alright, 1/4 to the x, and that's 1 over 256. Alright, fractions. I know you're going to have a heart attack, but I just want to go over here since I can erase. 4 squared is equal to 16. That's a 16. 4 to the third is equal to 64. 4 to the fourth is 256. So if you don't know it, just multiply on. But the idea here is that this is the same thing where I have 1/4 to the x is equal to 1/4 to the 4th power. So I can do squiggly line time, and I can go ahead and get my answer just like we're doing. And that happens sometimes with fractions, but does it always happen? No, and that's what I need to show you with the last 2 examples. So, any other questions, or not questions, but make sure you look at it and see what's going on before I erase. And I'm going to erase that quick way. Alright, so here goes. Boom, it's gone. So let's talk about example 4. example 4 is 2/3 quantity to the n power is equal to a 9/4. Now, if you were to take the 9/4 and rewrite it, that's the same thing as 3/2 to the second power. Because everybody remembers that if you have a over b to the nth power, I guess this is another property, this is a to the n over b to the n. You just raise each part to the power. All right, now, can I do squiggly line time? And the answer is no way can you do squiggly line time. You can't do it. You have to do something else. What do you mean I have to do something else? Well, the problem is that these two bases right here are not the same bases, but they only differ by a reciprocal. And it doesn't matter which one you do it to, but I'm going to go ahead and do this. If I take 3/2 and I take the reciprocal of it, that's like raising it to the -1 power. Now, am I ready for squiggly line time now? No, I have the third property of exponents to worry about. That's power of a power, so I have to multiply that, and so I get 3/2 to the -n is equal to a 3/2 to the second, and now they are the same. Now there's no more properties. Now it's squiggly line time, and so n is equal to a -2. Okay? Any questions? Or you can't ask questions. I'm in the classroom. Sorry. Take a moment to look at it. Now I'm moving on to the next example. All right. The next example is this. Example 5, and this is the last one for the page right here, and you get to try all those other problems. So when I start this particular problem, I can go backwards to 2 to the third raised to the 3x plus 2 power. And then this is the same thing as 1 over 2 to the fourth. But again, there's some issues here we have. We've got a power of a power for this left side, and we've got a fraction on the right side. And again, you can think of that fraction as 1 over 2 to the fourth or 1/2 to the fourth. It's the same darn thing. You say, why? Because 1 to the fourth is still just a 1, so it doesn't matter that I write the 1 to the fourth up at the top there in the problem. I'm talking about here, and I'm going to take it away. So I have a couple things to do. I have to do the third property of exponents, and then I have to do the reciprocal. So 2 to the -4 is the same thing as 1/2 to the fourth, or 1 over 2 to the fourth. And guess what time it is? It's squiggly line time. So I have 9x plus 6 is equal to a -4. I'm going to subtract 6 from both sides. Stray mark here. I don't want you to think there's another negative. It's just my hand making extra marks that I don't know how to fix. And then I divide by 9, and I get an answer of a -10/9. I promised I wouldn't pick her name anymore, pick her up, but we can do that. For all of you allergic to mixed numerals are wonderful. All right, I'm going to stop it. I'll have to call that guy back, and I'll do a part 2 for this.